A pump draws water from a tank and issues it from an end of a hose, which is 4 meters vertically above the level which the water is drawn. The cross-sectional area of the hose is 8 centimeters squared, and the water leaves at a speed of 6 meters per second. Find the rate at which the pump is working and take the density of water to be 100 kilograms per meters cubed. Right, so first of all, if we just draw a quick diagram. So what we've got a pump raising water going through a pipe here of 4 meters. We've got a cross-sectional area here of 8 centimeters squared. Notice the units are inconsistent. The water has been ejected from here at 6 meters per second. Okay, so we've got to make these units consistent, but we need to bear in mind the following. As the pump is being used to raise and eject the water at a given speed, then the total work being done is the sum of the potential energy of raising the water and the kinetic energy that the water has been ejected at each second. And if we got it at each second, then we actually have the rate at which the pump is working. Okay, slight problem here that these units are not consistent. So we know that 1 meter squared is 100 centimeters by 100 centimeters, which is 100 squared centimeters squared. And therefore 8 centimeters squared will be 8 divided by 100 squared meters squared. Right, so we will need to find the mass because we need mgh and a half mv squared for kinetic energy. So we'll need to find the mass of water being raised per second. Now, you can think, first of all, let's just find the volume of water in this pipe given any second, and that's being ejected any second because it's going at 6 meters per second. So we need to consider this, the volume being of water being raised and being issued per second will be 6 because there's 6 meters being ejected every second, so the length would be 6 times the cross-sectional area, this is a cylinder, which is 8 over 100 centimeters, 8 over 100 squared in meters squared. This is the cross-sectional area of this circle here. So it's like the volume of a cylinder, which is the cross-section times the height. It's not this height here, it's the height of this, because each second will be 6 meters being ejected. That will give me an answer of 3 over 625 meters cubed. Now we need to convert that into a mass using the idea that density is mass divided by volume, and therefore mass is volume times density. So in our case, the mass of water raised and issued per second will be our volume times the density. So mass is volume times density, which will give me 24 over 5 kilograms per second. Right, so the PE given to the water per second will be mgh. So that will be 24 over 5 times g times this h here, because it's been raised 4 meters, which gives me 188.16 joules. The KE given to the water per second is a half mv squared, so it will be a half times our mass, which is 24 over 5, times my velocity of the water is coming out, which is 6 squared, and that will give me 86.4 joules. Right, so the work done per second by the pump is going to be 188.16 plus 86.4. So the work done per second by the pump is going to be 188.16 plus 86.4, which gives me 274.56, so the power is the work done per second. Well, this was the work done per second, so the rate at which the pump is working is going to be 274.56 watts, and if we want to give that to 3 significant figures, that's going to be 275 watts to 3 significant figures. So this has been a video to show you how to find the rate at which a pump is working when raising water from a different level. I hope you've understood, and I thank you very much for watching.